Session 01 Celery Fundamentals. In modern web applications, optimizing server response time is critical to user experience. When a web server receives a request containing expensive work, synchronous execution blocks the entire request pipeline, reduces capacity, and leaves users waiting. Celery addresses this by providing an asynchronous distributed task queue written in Python. The problem is clear: synchronous processing blocks the request pipeline. When Unicorn receives a request with heavy work, the worker is held, capacity drops, and the user waits. Celery moves that heavy work outside the normal HTTP request response cycle and processes it in the background. The application returns immediately while the heavy work runs on a separate worker. Celery's core architecture uses message passing between three independent components. The producer, usually a Django, FastAPI, or Flask web application, serializes function arguments into a message and sends it to the broker. The message broker, such as RabbitMQ or Redis, temporarily stores and safely routes the messages. The worker is an independent process that continuously receives messages from the broker, deserializes the arguments, and executes the corresponding Python function. Here is a minimal working example. First, create a Celery application factory pointing to a Redis broker. Define a task with the app decorator. Then call it from a producer using the delay method, which never blocks the request. The call returns immediately with a task ID the client can pull later. A common early implementation mistake is using a relational database such as PostgreSQL, MySQL, or SQLite as the broker merely because it is convenient. A real broker uses high performance in memory structures and pushes messages directly to consumers. With a relational database, workers must poll continuously for new tasks. As the worker count grows, concurrent database queries explode, drive disk I/O to its limit, and effectively create an internal denial of service attack against the main application database. For task state and return values, Celery integrates a result backend. JSON is the recommended default for safety and broad support. Pickle supports complex objects but introduces security risks. MSCPAC offers high-performance binary serialization with very small messages. YAML provides clear structure but slower serialization. The runtime environment also requires care. Celery officially removed Windows support starting with version 4, so production systems should run on Linux or Docker containers. Why does polling a database as a broker collapse under load? A relational database broker has no push mechanism, so every idle worker must run a select for update style poll on a fixed interval. With n workers polling every few seconds, the queue table absorbs read queries even when there is zero work to do. This traffic competes directly with the application's real queries for the same connection pool and disk I/O. A real broker like Redis or RabbitMQ instead pushes the message to a waiting consumer, so idle workers cost nothing. Every delay call with a configured backend writes a result record. Without result_expires or an explicit forget call, a high-throughput producer can accumulate millions of stale keys in Redis or rows in a SQL backend. Set result_expires deliberately, the default is 24 hours. Alternatively, use ignore_result equals true on tasks whose return value nobody reads. Session 01 Recap. We learned that Celery moves heavy work to the background through message passing. The architecture has three independent components: producer, broker, and worker. Never use a database as your broker. Production runs on Linux or Docker. And always set result_expires to control backend storage growth. Session 02 will cover production reliability, including retry, backoff, and self-healing systems.